Okay, in Calculus Chapter 2, Section 2, we're going to look at limits. And the first problem is not, it's interesting, but it's not too bad. So it says, okay, calculate the limit as x approaches 0 of the function sine of 4 pi over x. So let's just break that down a bit. Limit as x approaches 0 of sine 4 pi over x. So the way you evaluate limits is you just plug in the number. So you replace x with this number. But here's the problem. You're going to get the limit as x approaches 0 of sine of 4 pi divided by 0. And I encourage you to try this with your calculator. Type 4 pi divided by 0. You're going to get an error. So any number divided by 0 is undefined. So we can't do it. So we've got a problem. So what this problem is going to do, and most of the problems in this section are going to say, okay, well, let's pick x as close to 0 but not 0. So we're going to say, let's pick some smaller numbers that are negative. So we'll pick like negative 0.0001, and then we'll pick positive numbers like 0.001. And you can do that. So you could type in your calculator the sine of 4 pi over negative 0.001, and you could type in your calculator the sine of 4 pi over positive 0.001. And you're going to get two different numbers out. And we'll do that, so we'll build a lot of tables where we pick these different x values, small negative, small positive, and we'll plug them in and see what happens. So what they want us to do on this problem is they pick the values for us. So they say, okay, pick x as 1. So you plug in 1 here, so you get 4 pi over 1, and if you type that on your calculator, the answer is 0. Then they pick 1/2. Well, 4 divided by 1/2 actually is like 4 times 2. It becomes 8 times pi. And sine of 8 pi is 0. So use radians on your calculator. You can try this. Pick 1/3. 4 divided by 1/3 is actually 12 times pi. Plugged into sine gives you 0. Plug in 1/4. So let me actually show that one just so you can see it instead of just listening to what I'm saying. If you have 4 pi over x, but x is 1/4, you would get 1/4. Well, 4 divided by 1/4 is 16. So you're going to get 16 pi. And that they just want you to type that 16 right there. Okay, and then they continue with this same idea. If it's 40 pi, you get 0. Oh, and this 16 pi was also 0. If it's 400 pi, you get 0. Any integer value of pi into sine is going to give you 0. Then they say try 0.0001. So you plug in 0.001 and you get 0 again. So all these numbers are pointing to 0, but the graph is anything but 0. So as x gets close to 0, in some cases it's positive 1, in some cases it's 0, in some cases it's minus 1. And it oscillates back and forth between those values. So something really crazy is going on here. So because this thing oscillates, it doesn't converge on one number, it goes up and down, we say the limit does not exist. Now, I think this is still very complicated at this stage. In fact, in grad school we did a problem like that was similar to this, and we kind of showed how chaotic it was because how it can change so drastically, even if you change your x by a tiny amount. So you change your x by a tiny amount and the answer goes from +1 to -1, just totally flips. So it's kind of a very chaotic problem. It's called a nonlinear problem. So we're going to have to expand on this idea of what does it mean to have the limit not exist? And we'll show you with some simpler ones, simpler problems. Okay, here's a simpler problem, I believe. So it says, Now our function is sine x over divided by x, and x is 0. Now if you plug in 0 here, you get sine 0, which is 0, divided by x becomes 0, so it becomes, if you plug in 0 here, you get 0 over 0, which is still undefined. So they built a table where they picked numbers, they did plus or minus numbers, and they started with 1 and they got the answer was 0.8. Then they went with a half and they got 0.95. Then they went with 0.4 and they got 0.97. They went with 0.3, plus or minus, doesn't matter, they get 0.98. 0.2 is 0.99. 0.99, 0.99, 0.9999, 0.9999, point a bunch of nines. What is it going towards? These numbers are getting closer and closer to positive 1. So the limit in this case equals 1. Even though this is not defined when x equals 0. In fact, it shows up on the curve as what we call a hole. So you got this nice sine curve divided by x, but then when x is 0, you get a hole because it's not defined there. Okay, but this limit does exist because from both sides your function's approaching 1. So this limit does exist. Because as I approach from the left, my value is approaching 1. As I approach from the right side, my value is approaching 1. They approach the same number. Okay. Where in that last one, they were going all over the place. It wasn't lining up. Okay, so that's problem 2. Okay, problem 3 is going to kind of test this idea of limits. So it says, what is the limit as x approaches 2? Okay, I got to explain that as well. So there's two kinds of limits. They have a limit of this function that they call g of x as x approaches 2 with a minus sign up here. That means, let me write this in words. This is the limit of g of x as x approaches 2 from the left. Which is to say, smaller numbers than 2. So your x values are going to be like 1.9, smaller than 2. 1.99, getting closer to 2, but not quite 2. 1.999, etc. Okay, but then there's another limit that reads like this. The limit of g of x as x approaches 2 plus sign. Well, this is all the same words except for it's going to be 2 from the right. So I don't want to write all those words. It's still the limit of g of x as x approaches 2 from the right. And so your x's are going to be bigger than 2, like 2.1, 2.01, and 2.001. So they're getting closer to 2, but they're still bigger than 2. Okay, so it's two different directions, left and right. So the first one says, what is g of x? From the graph, we see that the value of g approaches 2 as x approaches 2 from the left. So as x approaches 2 from the left. So I'm going towards positive 2. That's my goal destination, but I have to ride. This is how I teach this. You have to ride the curve. So I'm trying to get to 2 going left to right. I have to ride this blue curve. So I'm riding this. I'm going left to right, trying to get to 2. Where do I stop? So these are now lining up. And I care about the y value. So the y value, and I'm not psyched about this problem because it's confusing and they use the same numbers, the y value is also 2. So that's this 2 right here. Okay, then it says it approaches let me use color here, 1 as x approaches 2 from the right. So from the right, so now I'm trying to get to the same 2, but I'm coming from the right side. So I have to ride the curve, doesn't matter where I jump on it. I'm on the curve, I'm trying to get to 2 from the right side, I'm going towards this hole. So I hit the dashed line, which is x equal to 2, at this hole, and I go straight over, and I grab the value for the y, which is 1. Okay, this is what confuses students is you're moving left or right towards an x value on the bottom, but your eyes, you're tracing what's the y value of the function doing. So the answer I'm going to report is a y value. It's going to come from the y-axis, but I have to see as I'm approaching from left and from the right. And you can see that there's a mismatch here. 1 goes to 2, 1 goes to 1. So this limit's going to have a problem. So you can't have them approaching different numbers. Okay, in fact, it says, since this approaches 2 from the left, let me use the same color here so we can see it. This approaches 2 from the left and 1 from the right. Because those are different, then the limit does not exist. So you have to converge on the same number for the limit to exist. Now let's try the next part of this problem. It says, let's approach 5 from the left. So now they switch it to the x value of interest is 5. And we're going to attack this thing from the left. So from the left, I'm coming up to 5. And from the right, I'm going towards 5 from the right. They are both converging on the same value, and that value is 2 again. So this approaches 2 from the left, it approaches 2 from the right. Therefore, the limit, so let's see this. So we have limit as x approaches 5, in this case, from the left, that equals 2. We have the limit as x approaches 5 from the right-hand side of g of x, that also equals 2. So if that happens, we say the limit as x approaches 5 from either side equals 2. So notice, I have to be very careful about the way I write this. Minus sign means left, plus sign means right. If I don't have either of those, that's from either side. From either side slash both sides. So if they don't write a plus or minus next to the x value, that means from both sides I'm converging on the same number 2, and we have the limit exists. But notice the limit exists, but the function does not exist. The function is not defined at x equal to 5 at that hole. So what they do is they say, they put in a filler hole right here. So they say, okay, the limit from both sides is 2, but the actual function is equal to 1. So if I were to plug in x equal to 5 into this function, I guess they called it g, so let me get that right. They called the function g. If you plug in 5 in for x, you actually get the y value to be equal 1, which is what they wrote here. Okay, so I know this can be confusing. We're going to do lots of these, so hopefully it'll sink in as we go. Okay, explain what it means to say that the limit as x approaches 7 from the left, f of x equals 9. So let me write this bigger. The limit as x approaches 7 from the left of the function equals 9. So basically what that means is we have some function xy and we're approaching positive 7 from the left. So I don't know what my function is doing necessarily. It's in here doing something, but as I approach 7 from the left, the function is approaching 9. So as we approach 7 from the left side, my function is approaching the y value of 9. And here's the words: as x approaches 7 from the left, the function of x approaches 9. And then the other one they have is the limit as x approaches 7 from the left, f of x equals 4. Oops, sorry, no, right side. Let me get that back up here. So then they're saying, then they have written the limit as x approaches 7 from the right of that function equals 4. So I don't know what the function is doing, but as it's coming from the right-hand side, when it gets to 7 from the right, it's approaching 4. So we would have, as I approach 7 from the right side, the function is approaching 4. Now because these two are not converging on the same number, they're not doing this, they're missing each other, we're going to say the limit does not exist. So we would say, does the limit exist? No, the limit cannot exist because these limits approach different numbers. So if they're approaching the same number, the limit exists. If they're not, it does not exist. Would be the answer there. Okay, in problem 5, we're going to introduce infinity symbols. So this says the limit as x approaches negative 8. Now notice the difference here. If the minus sign's above the 8, that means from the left. If it's in front of 8, that just means negative 8, just like just a regular number. Of the function equals positive infinity. So here's what this looks like. I've got some function, minus 8 is over here. What this says is, and I'm going to draw a dashed line in here. As we approach negative 8 from either side, the function is going to go up towards positive infinity. So if your function skyrockets off to what looks like a vertical line, that's called positive infinity, and we don't write the positive. Okay, so the words are, the value of f of x can be made arbitrarily large by taking x sufficiently close to but not equal to negative 8. Okay, now in the next one, we have negative infinity. So the limit says the limit as x approaches 6 from the right side of the function equals negative infinity. Okay, so how does that look? Well, we're approaching positive 6 from the right, and the function itself is going to go down towards negative infinity. So as we approach, and I draw an arrow here because the function could keep going to the right for whatever it looks like. All I know is that as I move right to left, as I get closer and closer to positive 6, the function, the y value of the function is going to go down and down and down and down and down. So it keeps going down until minus infinity. Now, it could mean, there's a couple possibilities. It could also mean from the left-hand side it goes down to negative infinity, or it could actually go up to positive infinity. So it didn't tell me what the limit was 6 minus, which would have been the left-hand side, so I'm not sure. Okay, more practice with this. So in this, they give us a picture, and they say approach 2 from the left. as I approach positive 2, so again, I'm going to 2 from the left, writing the curve. My curve is going towards positive 3. So that's where I got that. Then it says approach 2 from the right. So as we approach 2 from the right side, I'm writing the curve and I'm approaching positive 1. Positive 1. Then, so does the limit as x approaches 2 exist? DNE means does not exist because these two numbers are different. So again, if they don't converge to the same number, the limit does not exist. Okay, what about the function when x equals 2? When x equals 2, I have two options. So basically, I'm looking at what are the y values of these 2 points. This is called a hole, and that's where the function does not exist. This is a filled-in hole. Or a point. That is a point on the graph. So between these two, you're never going to take a hole. That's not where the function exists. It's right here. And that value, that y value when x is 2 is 3. Because it lines up with 3. So that's where I got this 3. Okay, then it wants us to approach 4. So now we're approaching 4 from both sides. So from this side, it's approaching that hole. From this side, it's approaching that hole. And that hole has a y value of, again, I'm not psyched about that. The numbers are the same. They're not usually the same. They're approaching 4. So you get this 4 here. Now it says f of 4. Well, because that is a hole at 4, this does not exist. Okay, and that's problem 6. Okay, in problem 7, there's some more practice with negative signs. So the first problem says, approach negative 7. So as we approach negative 7 from the left or from the right, my graph is going down to minus infinity. Then it says approach negative 3. As we approach negative 3 from the left, the function's going up. From the right, the function's going up. That's going to positive infinity. How about 0? As I approach 0 from the left, my function's going up. From the right, my function's going up to positive infinity. How about 6 from the left? 6 from the left side is going down to minus infinity. And then 6 from the right side, the plus sign, from the right side moving towards 6, which means I have to move left. My picture is going up to positive infinity. Okay, these are called vertical asymptotes. So when we have some number where usually we show them as dashed lines, and if we use color, it's usually red. So at negative 7, negative 3, 0, and 6, we have what are called vertical asymptotes. Because your function is going straight up or straight down or both up or both down, and they're going to infinity. So these numbers are going to infinity. And you can prove these so you would say, okay, these are vertical lines. So x equal minus 7 is a vertical asymptote. That's the first one I drew. Then x equal minus 3, then 0, then 6. And basically what that means is this function, I don't know what the numerator is, but the denominator, one of them is x plus 7. One of them is x plus 3. One of them is just x. And then one of them is x minus 6. So we know you can't divide by 0. So x cannot equal 0, minus 7, minus 3, or 6. The exact same numbers that give us these asymptotes. Because if x is any of those numbers, I get divided by 0. But, and we can see this, if you pick numbers really close to these, then, like let's pick 7 for example. If you picked x equal minus 6.9999, it's going to give you 7 minus that number will be, so let's do this. This bubble right here would become minus 6.9999 plus 7, that bubble would equal 0.0001, which is a really small number. And if I divide that into any numerator, divide a numerator by a really small number, you get a big number. And if the numerator has a minus sign in front of it, it will be a big number with a minus sign, which means it goes down to minus infinity. There's a lot more to this. We'll study this quite a bit. But asymptotes show up when you're dividing by some quantity that if x equals that number, you get a divide by 0 error. And as you pick numbers really close to that number, your function will either grow really big or go really big negative. Okay, problem 8 is not too bad. It gives us a situation and wants us to pick the right picture. It says, as x approaches 0 from the left, the function approaches 2. So as I approach 0 from the left side, my function is approaching 2. Then it says, as I approach 0 from the right side, the function is approaching minus 1. So as I'm approaching 0 from the right side, my function is approaching minus 1. Then it says the function when it's 0 is equal to 1. So there should be a closed-in dot at 1 when the x value is 0. So this picture describes everything correctly. Okay, problem 9 is not overly challenging. It's a lot of calculations. So I highly recommend, if you have a calculator that can be programmed, that you Google how to program a function in whatever calculator you have. Because I can take, and I know these aren't allowed on tests, so, but I can take my TI-89 and I can program this equation, and then all I have to do is change the x value and it just spits out the answer. Microsoft Excel could do the same thing, so you could program this in Excel. I can show you how if you reach out to me if you're interested. But certainly for homework, I would rather you learn to do a little programming than to do this by hand. But you could do it by hand. So let me just show you one. So the function is x squared minus 4x over x squared minus 16. Then they change x to 4.1. So you're going to have to type in your calculator 4.1 squared minus 4 times 4.1 divided by 4.1 squared minus 16. And if you do this, you will get 0.506173. And they want 6 decimals, so you got to be real careful here. Then they change it to 4.05 and 4.01 and 4.001 and 4.001. So they're getting closer and closer to 4. And these numbers are getting closer and closer to 506, 503, 500, 5000, 5000. They're getting closer to 0.50. Then they say, okay, that's from the right. The numbers are bigger than 4. Now let's make the numbers smaller than 4. And you get 49, 49.6, 49.9, 49.99, and 49.999. Those are all approaching 1/2, 0.5. So, yes, these numbers are cumbersome to get, but hopefully you'll get fast with it with your calculator. It's not the worst thing in the world to sit down and do that. Okay, so that's how you do those. Okay, 10 says make a table just like the previous one to find the limit as the angle goes to 0 of sine 7 theta over tangent 4 theta. Now, we can do it with a table, or I would argue an easier way, we'll go to decimals. So we can type in sine parentheses 7x. So we won't use theta, we'll use x. Divided by, the other one was tangent of, parentheses, 4x, parentheses, enter. Let me make sure that was right. Sine 7 theta over tangent 4 theta. And you can just replace theta with x. And they want to see as x approaches 0, or theta approaches 0. So as you zoom in, the limit for this graph would be this value. So it's interesting. If you click on 0, it says undefined, because if you type in 0, tangent of 0 is 0, you get divide by 0 error. But you can clearly see there is an answer here. It is approaching this y value from the left and this y value from the right. So what is that y value? That y value is, you can click and drag. On the left, it's approaching 1.748, 1.75. And from the right, it's approaching 1.724, 744, 748, 75. So they're both approaching 1.75. So I would recommend you use decimals for that one to get this 1.75. It's a lot faster. In fact, let's use decimals for 11. It says, find the limit as x approaches 0 of x cubed times the natural log of x. So x cubed, x raised to the third, times ln parentheses x parentheses, enter, and there you go. So that's the curve. We want to see what this function is doing as we're getting close to 0. And as we get closer and closer to 0, this is getting closer and closer to 0. In fact, this one has the point 0, 0. So this one did work. So we get 0. The reason that one breaks down is if you type natural log of 0 in your calculator, you should get an error. But x cubed would be 0, so 0 times error. So it's kind of a question of, well, which would happen first. But we can see the picture, and it does approach 0. Okay, so problem 12, exact same kind of thing. They give you a function, and they tell you different x values. So you do have to plug in these different x values into this function, cosine 2x minus cosine x divided by x squared, and you'll get these things approaching negative 1.5. Let's actually see that one in decimals, though. So we have cos 2x minus cos x over x squared. How would I do this in decimals? I would type parentheses, cosine, parentheses, 2x, parentheses, minus cosine, parentheses, x, parentheses, parentheses for the top, divided by, and it was x raised to the second, I believe, on the bottom. Enter. Let me make sure that's right. That is correct. And we're approaching 0. Those numbers are getting smaller and smaller. So you can see as x approaches 0 from the right, it's approaching minus 1.5. As x is approaching 0 from the left, it's also the y value is approaching minus 1.5. So decimals could be a great way to get these rather quickly. It's not going to give you these 6 decimal numbers, so you would need a calculator to do that. But you could get it. Okay, and then, well, might as well, let's keep using decimals to get these. We can do it pretty quickly. So I have x plus 6, x minus 8 as x approaches 8 from the right. Now again, I can't plug in 8 in this denominator because I'll get divided by 0. So let's see what the graph looks like. It's going to be x plus 6, parentheses, x plus 6, parentheses, divided by x minus 8, parentheses, enter. I wasn't typing at all, that's great. X plus 6, parentheses, division symbol or backslash, parentheses, x minus 8, parentheses, enter. Let's make sure that's right. It is right. And we're approaching 8. So you can click and drag here. So as x approaches 8 from the right, notice from the right, as I approach 8, my y values are getting bigger. As I approach 8 from the left, my y values are getting bigger but negative. So this one from the right is going to positive infinity. Okay, for 14, 3 over x, secant x, perfect for decimals because it can handle trig functions so easily. So I would say 3 divided by x times, you can just type secant of x, parentheses, and there you have it. Now this one is approaching from pi, it's approaching pi over 2 from the right. Well, pi over 2 is like, pi is 3.14, so pi over 2 is like 1.7. Let me find it quick. So this is approaching pi over 2 from the right, and that pi over 2 as a decimal is 1.57. 1.57 is right, I'm looking at the first number, the x values, it is equal to right about, of course, well it's at this, it's where I have this asymptote. So this asymptote, you can't really, it's a little hard to see, but there's an asymptote right here at 1.57. From the right side, my numbers are getting negative. From the left side, they're going positive. So from the right, we have negative infinity. So I picked negative infinity for that. Okay, cosecant of x as x approaches pi. So I would just type CSC, parentheses, x, parentheses, enter. And pi is going to be an asymptote at 3.14. So we have, I wish I didn't do this in red, at 3.14 right here, there is a vertical dashed line, and they want us to approach from the right again. So from the right side going left towards this dashed line, my numbers are getting bigger and bigger negative. So again, we would go back and say negative infinity for that one. Okay, and then this one, you'll want to type this in decimals, and you'll get this top right picture. But I do want to show you how to solve this one by hand. All those other ones you can solve by hand, you just have to plug in values. So if it says approach x, pi over 2, well, you get pi over 2 is 1.57. So you pick a number smaller than that, 1.5, and you pick a number greater than that, 1.6, and you see what are the y values. Is it positive 20? Is it negative 20? What is it? And then you can pick numbers closer and closer to that 1.57, negative or smaller or bigger, and see what your numbers are doing. Are they getting bigger positive or bigger negative? So you can do all those by hand. But for this first part, I do want to show you how to find the asymptotes by hand. So to find an asymptote, you have to set the denominator of your function equal to 0. So we have 8x minus 5x squared. So to find asymptotes, you set this equal to 0. Because you can't divide by 0, so it's going to tell us the x values that make that become 0. So we set the denominator equal to 0. We can factor out a common x. This will be 0 if this is 0, so if x is 0, or if this one equals 0. So we set that one equal to 0, add 5x to both sides, divide both sides by 5, and these two x values are the vertical asymptotes. So x equal to 0 gives us this vertical asymptote right here, and x equal to 8 over 5 gives us that vertical asymptote right there. Okay, 17 is pretty similar to the first problem that we looked at. It's sine of pi over x. So if we type in decimals sine, parentheses, to get pi you just type pi, divided by x, parentheses, we get that same oscillatory motion. So as x approaches 0, this thing is going up and down like crazy, and so the limit does not exist because you've got this thing approaching different values as you go from left and as you go from the right side. So we would say, no matter how many times we zoom in toward the origin, the graph of f of x appear to consist of almost vertical lines. This indicates more and more frequent oscillations as x approaches 0. Yeah, so what they're telling you to do is on your graphing calculator, zoom in. And as you're zooming in, you just see this infinite, I mean, this is kind of crazy, this infinite up and down vertical lines. So a very chaotic system. Okay, then the second to last problem is a theory of relativity. States that your mass, so as you accelerate a mass, it actually gets heavier. So your mass is equal to your starting mass divided by 1, the square root of 1, minus the velocity you're going divided by the speed of light squared. So if you were to be able, let's actually show this. So if, it's kind of neat. If you could get the velocity you're traveling to equal the speed of light, then your mass would equal m0 divided by the square root of 1 minus v squared now becomes c squared divided by c squared. But anything divided by itself is 1. So you get 1 minus 1. You get the square root of 0, which is 0. You get your mass, your initial mass divided by 0. This is technically infinity. Because if I picked, let's say my mass, let's say I wasn't going the speed of light, let's say I was going really, really close to it, then this would be a really small number. So it'd be like 1 minus, actually it'd be a number close to 1. So let's say I got that to be 0.999. So I'm going like 99% the speed of light. Well, this is going to give you 1 minus that is going to be 0.001. And if I take a square root of that, we get 0.0316. And if I divide that into 1, we get 31.62. So if your mass was 100 kilograms, now you're 3,000 kilograms. So you're 31 times more massive in a relativistic sense. And so this basically is kind of means that to travel towards the speed of light, only thing that can go the speed of light is the speed of light. So if you have any mass at all, the energy required to accelerate you to the speed of light is astronomically high. So it's kind of proves again that there's this upper limit of the speed of light for velocity. So as your velocity approaches the speed of light, your mass will approach infinity. It will get bigger and bigger and bigger. Okay, last problem. Determine whether the statement is true or false. If the line x equals 3 is a vertical asymptote of y equals f of x, then f is not defined at 3. The only reason that this is wrong is because they did not put f is not defined at x equal to 3. If they said f is not defined at x equal to 3, then this would be correct. But they did not say that, so that means at x equals 3, you could have a vertical asymptote, but is not defined at 3. Well, maybe they're talking about y equals 3. Maybe they're talking about y equals 3, not x equals 3. And my function looks like this, something like that. Well, sure, it's defined at 3 right there. So they weren't clear enough. You have to be clear when you state this. And that should conclude Chapter 2, Section 1. That should conclude Chapter 2, Section 2.